here. The second time delay, the time delay between second and third pulse, we call it population time, capital T here. And the echo time, actually, we didn't measure this time. This signal here is measured in the frequency domain, so we get omega T directly. And we can actually scan, in a real experiment, you fix a population time, you scan coherent time to get a map like this. So this is the scanning of coherent time. For each coherent time, you have a heterodyne detected spectrum. And then you Fourier transform along this tau, and you get a two-dimensional spectrum. So this two-dimensional spectroscopy contains very much information on the dynamics of a system. For example, on the diagonal, you see the states where it absorbs and emit at the same frequency. But if you have an off-diagonal peak like this one, it means you absorb at a higher frequency, higher energy, and emit at low energy. So during the population time, this system goes through some energy transfer or relation dynamics from this high energy state to a low energy state, indicated by this closed peak. So this is very informative. You can also see a lot of different dynamical informations in this two-dimensional map, and I'm not going to go into detail here. So conventionally, to simulate this kind of 2D spectrum, you can employ a density matrix-based method or wave function-based method, and there are several different approaches. I'm not going to go into a detail. Some of the audience in here actually know HEOM, and HEOM can also be applied to calculate this spectrum. And here we try to implement a wave function-based method that employs so-called quantum Schrödinger-Langevin equation approach. So our approach is like this. We want to propagate the wave function of a system. And the wave function of a system is governed by some system Hamiltonian, and some friction operator, and some matter field interactions. Okay. So we specifically model dissipative dynamics using a Langevin approach and the light matter interactions in our calculation. And this F friction operator is obtained or derived from quantum Langevin equation, specifically for some vibrational states. And this HINT, this light matter interaction, includes 3 laser pulses. Okay. And the details about this friction operator, it looks like this. Basically, it's a drag force and random force over the environment acting on the system. And this is the system position operator minus some its average average position. So this is some force times distance. So this is the environment, including this drag force and the random force, the work that environment performed on the system, basically. So this is the friction operator. It yields the realization dynamics of the vibrational manifold. Also the electronic manifold also, yeah. And we want to treat light matter interaction. But this is not that trivial in this case, because we want to simulate signal coming out from a specific phase matching direction. Okay, so we cannot just use 3 pulses and interact with it. We need to do phase matching. And by a perturbative approach to derive this interaction of this interacting Hamiltonian and the system, we can find out that photon echo signal actually depends on 4 terms. And all these 4 terms can be evaluated if we propagate 10 auxiliary wave functions, basically with different non-Hermitian system field interactions here. So with this approach, we can now calculate a specific photon echo polarization and calculate 2D spectrum. And this approach is not limited to a specific method, specific experiment. If you do electronic 2D, electronic vibrational 2D, vibrational IR 2D, it's all the same. So this is a very general approach that can apply to various systems. For example, this is a 2D ES electronic spectroscopy on displaced oscillator simplest model we tested with, and you can see the simulated spectrum at different time delay, and it actually contains beating signals. And in this case, we were able to use this peaks amplitude beating to figure out or separate ground state and the static state coherences. So basically, our prediction is by looking at different cause peak and diagonal peak phase quantum beating signals, you can look at specifically at vibrational coherence in ground state or in excited state, and that's something that you cannot clearly distinguish using conventional pump probe experiments. We also use this approach to simulate IR, 2D IR spectrum of tag hydronium ions. So this is a hydronium ion, and in molecular beam experiments, people can actually tag this hydronium ion with different tagging molecules. For example, you can tag it with argon or nitrogen. Okay, and we can simulate the spectrum, linear spectrum, and compare to experimental results. And with those information, we can actually simulate its two-dimensional IR spectrum. And this two system actually shows very different two-dimensional IR spectrum, because in argon tag system, there is very strong Fermi resonance over the hydronium bending mode and OH stretching mode. So in this case, this quartet square pattern emerges. But in the N2 tag system, there is no such strong coupling, so you don't see those quartet system. So in this case, we predict that two-dimensional IR experiment could be a very useful probe to detect this kind of Fermi resonance signals. Another thing that we want to apply this technique to is to look at some non-trivial, non-adiabatic dynamics in molecular systems. And the most important one, or most famous one, is this conical intersection dynamics. It have drawn interest from many, many different groups, but the key thing here is the experimental or theoretical calculation of a conical intersection are often indirect, because in those experiments, normally they look at near degenerate states, but no information of a Berry phase. But we know that the key of conical intersection dynamics is this Berry phase effect. So we want to ask if this 2D dynamics can be used to probe this Berry phase. So the idea here, we utilize a 3-state 2-mode model. It's actually a parametrized model for this Parazine system. There's a tuning mode at this frequency, another coupling mode at this frequency. Basically, Hamiltonian or the potential surface looks like you have a ground state and 2 excited state, and there is a conical intersection here at this excited state, between excited state 1 and excited state 2. And we are doing theory, so we can compare 2 different models. One is the model have linear coupling here. So this is a real conical intersection system. And we can actually use a constant coupling, small constant coupling here. And this is a very closing model. So we want to obtain information about conical intersection specifically, and we'll compare these 2 kinds of different models. Now, those are, so I can skip this. So we simulated 2-dimensional electronic vibrational spectra of both systems. So 2D EV is a technique in which you pump at the electronic excitation and probe at the IR excitation. And this should be the most informative technique to look at conical intersection dynamics. So if we simulate the 2D EV spectra for this conical intersection system and this avoided closing system, you clearly see that the 2D spectrum actually looks very different. Okay, so there are signatures of conical intersection dynamics in the 2D spectrum. And if we take the different population time and do a Fourier transform to obtain so-called 2-dimensional 2D EV bit map, okay, and we see something like this. Okay, so this is a beating signal, frequency of the beating signal at for these 2 different systems. And they are very different. But we can see a difference, but we cannot understand. We do not understand where the differences come from. Basically, we cannot interpret those results. So the question we ask is, how do we look at these 2D EV results? And our proposal is, we should focus on IR signal probe at a given visible excitation frequency. So the concept is this. To look at this quantum dynamics in the excited state manifold, you should look at a specific excitation and look at how vibrational dynamics propagates on this excited state potential surface. And this can be resolved in a 2D EV signal by specifically look at some initial pump frequency, okay, and generate a two-dimensional map of